So today I'm going to be talking about code generation with llvm-hs. A little bit of background about myself. I spent most of my career kind of working in numerical computing in various forms. Most of my time was spent working in the financial services sector, where I worked on a lot of trading systems and pricing algorithms. So I've seen a lot of interesting things in the financial sector, mostly a lot of bad code, but a lot of code that has to run particularly fast. So I spent about 4.5 years working on pricing algorithms and trading systems inside of some Wall Street banks. And so I saw a lot of things that were written with C++ that didn't necessarily need to be written with C++. I know this will be blasphemy if there's anybody from the C++ conference here, but and so I ended up picking up the low-level virtual machine framework quite a bit. And so I developed an interesting set of skill sets around that. And then when I started working in Haskell professionally, I had an interest in working with llvm just because it's a great compiler toolchain for building custom languages. And so I figured I'd talk about that. So I maintain a library called llvm-hs, which is a wrapper as well as several sets of layers of abstraction on top of the C++ bindings to Haskell. It has a variety of tools that are useful for building native compilation frameworks for embedded domain-specific languages, as well as full-on ahead-of-time compilers. So llvm, probably the worst name ever, because it is low-level, but it's not a virtual machine. So it stands for llvm, it stands for low-level virtual machine, but it's around a 15-year project, started at the University of Chicago. It has no virtual machine inside of it at all. It's effectively just a compiler framework for C-like languages. But it's a very, very convenient computational target for a wide variety of languages, including functional programming languages. It provides about a very nice library form of about 30 years of research around all the things that consist of building a backend compiler. So if you're building a new compiler today, it is definitely worth taking a look at the llvm framework, because it provides a lot of things out of the box. So llvm-ir can be thought of as basically 3 equivalent representations of some program. So there's the in-memory C++ data structures, which are C-like structures that hold all of the instructions, the modules, and all of the data involved in a llvm program. There's also the bitcode, which is a binary serialized format of llvm-ir. It's useful for loading and serializing into disk, as well as being used inside of the JIT, and also the human-readable textual IR. So the bitcode files are .bc, and the text files are .ll. So if you happen to have the Clang framework installed, which is installed by default if you have a Mac, or it's just an apt-get install way if you have a Linux machine, you'll have all of these programs by default. You can try them out. You'll have the clang compiler uses llvm behind the scenes. So if you want to convert between any one of these representations, there are command line tools to do that. So what does this look like under the hood? So you have a C program. It says int main return 42. You can ask Clang to output the llvm-ir, and it looks kind of like this. So the top level bit of it is a description about the assumptions about the architecture that we're running this code on, how data is laid out in memory, what's the size of a pointer, what's the maximum size of a register, and then what's the target. So in this case, I'm compiling it on an x86 64-bit machine. There's a certain set of metadata about maximum size of an integer being 64 bits, and a bunch of other metadata about what's the smallest size of numbers like I1. And so then we compile that into IR, and we get this define I32, main, no unwind, ret I32, 42. So that's the llvm-ir representation of this C program. So it contains all of the information needed to fairly accurately compile the C program. Most of the stuff is metadata, so I'll kind of walk you through what is the structure of the language itself before we delve into how do we target it from inside of Haskell. So the llvm ecosystem itself is used for, I'd say, the 4 big languages here: Swift, Rust, Julia, and Haskell. GHC Haskell in particular. They all have an IR backend in some form or another. Particularly Swift and Rust use it very, very heavily. Haskell has an llvm backend as well. It's a little, it's a little odd in some cases, but it gets the job done and does certain numerical code quite quickly. So talk a little bit about llvm-hs, the Haskell library that I maintain. So if you happen to have your computer open and you want to download the repository, it's at this GitHub URL. It should be able to run out of the box, either using Cabal, NoBuild, Stack, or Nix. So we have all 3 packaging systems. This should be, so a little bit of historical context on this library. This is actually a fork of a very, very old library called LVM General, which was kind of abandoned about 4 years ago now. So we kind of picked up maintenance of this library and kind of have updated it to support modern versions of LVM. So everything from 5 onwards is well supported now, and it should basically build out of the box with all of the standard tooling. So if you tried old versions of this library, I think you'll find that you hit some rather inconvenient roadblocks along the way. They should all be streamlined now, so it's definitely worth taking a shot. So why do we want to even have this library? Typically the problems I was working on inside of my job, we typically would have some high-level description of some program or some mathematical kernel or some solver function or some data processing or stream processing utility that needed to run a lot faster than was available during the being embedded inside the host language. So basically we wanted to have native C-like execution speed for data processing, but we wanted to have the ability to dynamically generate these things on the fly. So typically we'd have some formula that would be imported by the quants. It would be described in some sort of high-level domain-specific language, which would describe some sort of transformations over a certain set of cash flows. You'd feed that off to some solver, which would calculate some sort of optimal portfolio based on all of these cash flows, and then it would give back a number which says, okay, you should weight your portfolio in a certain amount of ways. So these kind of problems were highly dynamic. You couldn't generate the code ahead of time because it had to work interactively, and you needed to run fast. So these kind of projects structurally look like compilers from a high level. You're taking a syntax tree which describes some sort of logic or some sort of sequence of transformations, and you want to produce the most optimal code that's going to process the inputs and produce some outputs. This can run from anywhere from a few microseconds all the way down to big data processing pipelines, which would take hours to run and crunch over massive terabytes of data. So and LVM kind of adapts to both kind of frameworks. So I'd say the 2 big problems you use LVM for, and you approach these 2 problems in kind of slightly different ways, is you're building a compiler. So think of your favorite ideal language that you want to build, and you write that in Haskell. You have all this wonderful pattern matching machinery. You have all of this wonderful parsing utility. You have this type checker, and you want to basically output the end of the day so you can generate native code, so you can run your code on any kind of modern CPU. So this is a classic problem. So the more non-standard one, the one that I kind of worked on most of my job, was this problem where we have a domain-specific language or an embedded domain-specific language, which is some Haskell-like thing which we've embedded in some sort of monad or some sort of well-typed AST. We want to synthesize a fast representation of, and so LVM adapts to this as well. So we can basically hook the llvm-hs JIT compiler into the Haskell runtime so that we can generate arbitrary code fast on inside of the Haskell runtime, and then call it and invoke it from inside of the Haskell runtime system. So this is quite useful. It allows us to have a lot of the benefits of just being able to generate arbitrarily complex math kernels on the fly for numerical computing purposes. So what does that look like? Effectively, since the LVM JIT is running inside of the same process as GHC or GHCI, we can share objects across the runtime. We can also have LVM borrow the GHC allocator and use anything that's already linked in memory. So LVM and GHC can talk about the same data structures under the hood. They can talk about the same representation of integers. They can talk about the same representation of all the native types and move data back and forth between the GHC runtime and Haskell. We can also dynamically link arbitrary libraries on the fly, just using standard Unix utilities. And that all works quite well. So what does the LVM toolchain actually give us? It gives us a lot. So in principle, and I've done this, I've written a blog post about how you can write a custom JIT compiler on the fly. If you go down that path, you're going to find you're going to hit up against a lot of things that you're going to have to implement from scratch. Things like instruction selection or graph coloring problems or all sorts of things that are basically exist out of the box and built on about 15 years worth of work in the LVM toolchain. So particularly around optimizations, the stuff's really not terribly useful to re-implement continuously, and that's why LVM kind of exists today. So particularly register allocation, instruction selection, cross-platform targeting, fast compile times, reusable optimizations, and it's just an extensible framework. And the optimizations you want to kind of use for a lot of standard things are dead code elimination, loop invariant code motion, strength reduction, loop unrolling, instruction combination, automatic fusion, and automatic recursion detection. So all these things you kind of get out of the box with LLVM, which is wonderful. On the top of the fact that you also get a retargetable language that you can target to ARM, x86, RISC, all with the same IR sitting in between. So you get all of these platforms at the back end for free. Nice. So what does instruction selection look like? On the left, you see the IR form of a simple add and XOR kernel, and then LLVM will take this, process it, and produce the assembly code for whatever platform you want. So let's walk through a little bit about the language. LLVM is not the tiny language it used to be. It's actually quite large now, but at the heart of it, there's a very, very simple kind of small core. So I'm going to walk you through kind of the basic primitives, just enough to kind of get up to speed so that you can read kind of IR, and then we can talk about how we implement that in Haskell. So what does the type system look like in LLVM? It's sufficiently, hello? Here we go. The type system in LLVM, like its namesake implies, is very low level. It consists basically of machine types. So on the left here, we have I1, I8, I32, I64, float, and double. These are your kind of standard x86 machine types. LLVM also supports arbitrarily sized integers that will kind of do instruction selection so that they process the memory just like it was an integer up to an arbitrary size. So you can technically have like 128-bit integers, and LLVM will figure out how to do those operations for you. So it abstracts over all of the hardware details of the compiler of the CPU, and kind of gives you an interface that kind of works across every CPU. We have array objects, which are basically packed sequences of memory, which consist of a single type. We have structures, which are basically packed heterogeneous type objects. So they're packed data. Nested structures, so you can nest structures together, and you can also nest arbitrary sized floats and vectors inside of structures. So think of like packed memories of heterogeneous things. You also have vector types, so there's a double and a float, and there are 4 of them or 8 of them. So the 4 is the 4 vector, and then the 8 is the 8 floats packed together. So these are useful because most modern CPUs have the ability to operate over memory in bulk, and certain instructions to do explicitly just that a lot more efficiently than operating over them individually. There's also pointer types, so pointers to a float or to an aggregate structure. So what are the basic structures? This slide's basically just a giant lie, but there are a lot more than that, but these are kind of the basic ones that are used in a lot of the simple programs. So shifting, binary operations, arithmetic, and then control flow instructions. So I'm going to walk you through a little bit about that. And then variable names inside of LLVM. There's kind of 2 types that you'll see. So if you look right here, you have a @, which is a global definition. It defines a symbol that's available across the entire module. And then we have these ampersands, which are local variables that are scoped within a single function. So this defines a block, which is a function defined inside of a module. And then it defines a sequence of instructions which operate over either global variables or local variables scoped to the function. So global symbols always have a pointer type. And then the body consists of a sequence of instructions that operate over local variables. And then at the end, there's a terminator, which defines how the function yields a value. So the basic block structure, like I said, is a function definition. It has a block name, which is a sequence of kind of named jump statements, and then a body of instructions, and then a terminator. So that's the most basic structure inside of LLVM. All LLVM instructions are in single static assignment. So this is quite natural to us functional programmers, but it effectively just means that you don't ever write to a reference more than once. A variable is assigned exactly once, and every variable is defined before it's used. So in C, you're probably quite used to defining a reference to a value and then updating it in place. In LLVM, everything is defined as creating a new value and then performing operations which also produce a new value. So this is called single static assignment. You can think of it as basically just natural functional programming. So what does that look like for conditional statements, for instance? If we have a statement like, if x is less than 5, assign x be x plus 1, else x is equal to x plus 2. So this is not necessarily natural to write inside of a functional kind of single static assignment form, but there's this notion that we can add to the language called a fee node, which basically dispatches on the location that a jump or an instruction came from. It allows us to assign a value based on where it came from. So this x3 is defined to be one value if it came from the first branch of this if statement, or another value if it came from the second one. So I'll show you an example in a second, which will make that a little more clear. So what does branching logic look like inside LLVM? On the left, I have some sort of some code, which describes a simple LLVM program, and then on the right, I have a description of the control flow graph. LLVM has a bunch of utilities for taking an arbitrarily sized module and outputting all of the control flow graph in this graph-viz form. You want to visualize it. So the simplest one is basically just a simple function with one basic block, which just returns a value. The next one would be an unconditional branch, which defines 3 basic blocks, an entry, next, and a return, and then progresses from entry, which branches to the next, which branches to the return, which just returns a 0 value. So it goes from start to next to return. Oh wait, sorry, this should be start here. Sorry. Anyways, and then the conditional branch statement allows us to branch conditionally on a specific value if it's true or false. So you can think of this as a very low-level primitive for implementing if statements. And then here we have a start block, and then 2 left and right blocks, which both have a terminator, which yields a specific value based on whether the branch condition is true or false. So what do switch statements look like? You can think of this as kind of a low-level pattern matching on LLVM types. An entry block here, which has a switch statement on a specific value, namely the input A, and then branches to a specific label based on whether the value A is 0, 1, or 2. So here we see, or also a default statement as well. We have the switch statement, and then it branches to either one of these 4 basic blocks, depending on what the value of the switch statement actually is. So it's quite useful. And then the fee nodes, the most complex thing. Here we have a function definition foo, which branches based on a condition, and it branches either to a left or a right, based on whether the condition is true. And then in the left statement, it'll perform some operation, which is iterating or incrementing an I variable. And then it will branch to a merge point, which looks at the value +1 and checks whether it is a specific value. If it reaches -1, it will branch to the right, which will then branch back to merge. So this is basically a very, very low-level way of implementing loop operations that can so this is basically used to implement loop operations. So the fee node here is exactly the one I showed you before. So this fee node will look at the value based on where the statement came from, where the last instruction came from, and then yield a value join, which is either one of these values. So probably the most complex concept in LLVM, but not terribly, if you kind of think of it as basically just a loop statement reversed. So then we have this count function, which is kind of just a simple increment to n. There's some more instructions here, but it's basically just, this is what a simple or I in ... to n looks like inside LLVM. So how do we start implementing these things in Haskell? Oops, there's a little typo here. There's an llvm-hs provides a variety of monads, which you can basically use to synthesize all of the llvm-ast in pure Haskell, which generates an arbitrarily complex abstract syntax tree, which describes all of the LLVM. And this is kind of embedded recursive do monad here that allows you to define all of these function statements, all of the basic blocks, and then compose them together in a nice kind of monadic interface so that you can synthesize your IR on the fly. So this is a pure Haskell representation, so none of this requires any C++. At the end of the day, you can dump out the llvm-ir, you can introspect it, you can tear it apart and compose together individual kind of sub builders together to produce like higher level constructions that you can use to synthesize more complex IR. So if you wanted to say have a closure IR builder, you could do that, which would abstract over variety of ways of combining LLVM instructions. So it's a very, very convenient interface. And so what does compilation look like when you're building this for a little language inside of Haskell? So say if you have a little functional language which is describing a Fibonacci number, you take some abstract syntax tree, you walk over it, you describe it in some sort of form that's amenable for compilation, and then you walk through and generate this llvm-ir using the llvm-ir builder inside of Haskell, and then you get this dump of the representation of that logic. You then call the llvm-hs bindings, which will then allow you to produce the assembly code for that representation, and then you get a nice optimized kernel that you can call from inside of Haskell. Okay, so let's talk a little bit about what optimizations you get for free inside Haskell, inside of llvm-hs. So the mem to reg pass is probably one of the most important ones inside of LLVM. It basically allows us to define an arbitrary number of allocations on the virtual stack inside of LLVM. So inside llvm-ir, we have an arbitrary number of definitions, and then LLVM will figure out how to shuffle all of this data and assignments and references in and out of memory in the most efficient way possible. So this is a pass that's run after you generate your RI. So the nice thing about LLVM is that you can basically throw really, really suboptimal code at it. Like you let your compiler basically just emit the dumbest possible thing, and then the LLVM just kind of just optimize away all of the allocations as much as possible. So in particular here, this is allocating 2 pointers, and then loading a value into them, and then returning that value. But there's a lot of like shuffling things in and out of memory that are unnecessary when this actually just results in just one operation. So LLVM is quite clever, and it'll just figure out how to compress all of those things together and then just return what the logic would be in the most efficient way, such that you don't read or write from memory as much, and just do everything in registers as much as possible. Also, instruction combination is quite non-trivial to implement inside of a. There's a lot of them that you can do. So like this law a la De Morgan here is baked into LLVM by default. So in particular that x and z XORed with y and z is actually x XORed with y and z. So LLVM is actually aware of a lot of these things. And when we have to AND operations, LLVM will say, okay, I know a symbolic way to simplify this using a set of formulas that I have internally, and I can reduce this IR so I'm doing one less CPU instruction. And it can run through your entire program and apply all of these things in bulk. Auto-vectorization is probably one of the more compelling things for numerical computing. So in particular, when you're generating things like solvers, for instance, you want to make sure that the entire reason for doing this is that we're getting really, really efficient code that's using SIMD, AVX, SSE instructions, so that whenever possible, when we're doing operations over, say, loops, we're not doing a single element instructions, we're doing them over bulk vectors of data instead of individually. So modern CPUs have a lot of clever specific instructions for generating these things that even GHC does not know about. So GHC's story for, say, doing SIMD selection, instruction selection is not particularly great at the moment. But if you call out to LLVM and you annotate your functions in a specific way, you can get code that can be 2 to 3 orders of magnitude faster than what GHC can generate. Just because it has more metadata about how the loops are structured, what data it's operating over, and can make like simpler assumptions about how to generate the code. Okay, so last year, in addition to forking llvm-hs, I was hacking on llvm-hs with Joachim. He's right there. We ended up working on a really, really cool extension to llvm-hs, which I thought was quite interesting. So a lot of this is his ideas, actually. So, and this provides a new interface to llvm-hs, which if you're keen on doing type-level programming and embedding semantics of other languages inside of Haskell, this is a really, really cool project. So I'm going to describe briefly how we kind of went about doing this. So the problem with C++ is that oftentimes if you operate with LLVM, you'll hit up with this quite often. So LLVM is really, really good at doing things really, really efficiently, but it also does not particularly fault tolerant. So if you happen to construct malformed IR, or worse, you try to construct malform or execute malformed IR, you'll hit up against a lot of segmentation faults. So when we're operating with this in Haskell, like the natural disposition for us Haskellers is to kind of assume, okay, this is a type safety problem. Why don't we just enforce more of the correctness guarantees about our IR construction at the type level and make sure that we get IR that's correct by construction, or at least has well-formedness constraints before we start offloading it to C++, where this nasty stuff can happen. So the answer is obviously more types. This is a Haskell conference after all. So GHC has a lot of machinery these days that we can use to kind of embed enough of the semantics about LLVM itself at the type level so that we can kind of enforce stronger guarantees than just exposing just a raw AST that you can synthesize as arbitrary as possible. So for instance, in the llvm pure AST, we currently allow you to, say, do an add operation over an integer and a floating point value because the AST itself does not actually enforce that. So you can construct this, you can offload it to C++ bindings, and you'll find that the thing's like false, which is not great. So a lot of these things can be eliminated with just richer types or GADTs, but you'll find a lot of things require a lot more complex machinery at the type level. So for instance, if you want to assure that when you're indexing into a structure that you always get back the specific value that you're indexing into. So if you're indexing into a packed structure, which is an int and a float, you want to have a type level representation of that structure so that when you index into the 0th element, you get the int, or the 1th element, you get the float. And you want to have your type system be aware of that so that when you do these things, you get well-formed results, or you cannot construct malformed IR. So effectively, this is all of the things you need to represent LLVM types in Haskell data structure. So we lift these to the type level using data kinds. Integer types are indexed by a nat, which is a type level natural. Pointer types are recursive on the type itself, so you have a pointer type to another type. And then we have function types, which are a return type, and then a list of argument types. Vector types are indexed by a type level natural, which is the size of the vector. So how many elements there are, 4 or 8 typically. And then a structure type is a Boolean, which is whether it's packed or unpacked. And then the list of types, which are the constituent elements of the packed structure. Okay, so now we're going to do something a little clever and a little evil. We're going to create this new type, which actually, funny enough, overloads the triple colon to be a type level type annotation, if you will, which if we define a new type, which is polykinded on the index, and then we have this typed constructor, which is typed. We'll also define this triple colon type operator, which is a non-polykinded variant of the 4 colon operator, which is specifically for the type that we showed here. So the polykinded one works for any kind of structure, or any kind of type you want to plug into the K parameter. And then this one is specifically specialized to the LLVM type. And then we have these 2 operators, which basically pack and unpack the triple colon type annotation. So that was what we use to enrich our LLVM types with metadata or type level type annotations about the LLVM types. So then how do we work on embedding LLVM semantics inside of this type annotation? We created this type class called known, which is also polykinded, which says, okay, given a type level annotation, can I produce a value of that specific type? And so we use this to move back and forth between our type level LLVM type annotations and the value level LLVM types. So we have basically a conversion system, which is a type family, which moves from a known value k down to the value level to produce a natural, which is manifest as an integer, or type level natural to an integer, a type level symbol, or a type level string, down to a value level string, as well as a type level name to a name. And then we have some conversion utilities for basically moving back and forth between the type level annotations about integer types and vector types by basically just pulling down the index for the vector type and then the type of the vector itself. So if you have a type level vector of natural number 3 and a int at the type level, this will move back to the value level to be the integer 3 and the value level LLVM type of integer. And this has a nice seamless semantics to allow you move back and forth between the information you have at compile time and the information you want at value level for generating the code. Okay, and then for vectors, structures, and pack structures, we need a little bit of like type level list machinery, type level vectors. So there's, we define this other evil type level operator, triple colon star, which is a type level heterogeneous list of LLVM types, which can be indexed into. So we take, and then we just find this pattern matching, pattern synonym at the type level that allows us to recursively unpack these type annotations and pluck out the single values that we need to when we index into the structures. And we have a pretty standard natural indexed vector object that we can construct recursively by a cons operator at the type level. So pretty standard machinery. And then what do we get for all of this machinery that we have? Okay, so basically, instead of exposing this add constructor, which is the kind of underlying untyped, unsafe AST, we can construct this smart constructor, which says for all widths of the same type, so we have this width scoped over the entire definition, we have a constant with a type level LLVM type annotation of integer type of that width, and we expose the add to be basically polymorphic in adding any two like integers and producing a resulting constant which is of the same output. So this polymorphically, it works over any kind of LLVM type, integer type, where width is the type variable. And we get a type-series interface that enforces the kind of correct by construction IR that can be built. And now for structures, things get a little bit more complex, but not terribly. Basically, for structures, we basically have this heterogeneous list of LLVM types that are indexed on the element in the structure. So we have the 0th element. The resulting type of plucking that value out should just be that we get the 0th element type. And so we can use GSC's type-safe course to kind of just give us a type-safe constructor for constructing and tearing down LLVM structures in a way that enforces that we can't misuse values. So llvm-hs type is kind of an open project we have. Like I said, I kind of hacked on it last year at ZuriHack with Joachim, and it's a really, really compelling interface. I haven't really touched a whole lot since ZuriHack last year, but we definitely have ambitions to basically guarantee a lot stronger guarantees about IR construction than we can do in C++, and Haskell's kind of the perfect medium by which we can kind of explore what the right interface is for that. So if you're keen on hacking on that, I'm going to be working on that at ZuriHack again this year. Some open problems. How do we build a strongly typed IR builder, for instance? How do we build a monadic interface that enforces that modules have the right properties around their argument types and return types? How do we map that to the type level? How do we enforce well-scopedness at the type level? That's an interesting problem. And how do we basically support a larger set of the LLVM instruction set, particularly around how do we do all of the vector operations and how do we do all of the atomic and parallelization instructions in a way such that we keep track of which values are being applied atomically, which ones are being parallelized, so we can keep track of all this metadata and enforce that when we do use some of the more advanced features of LLVM, we're using them in a correct way. And also basically just having a really, really great interface for the vectorization utilities, because most of the use cases for llvm-hs revolve around numerical computing. And so the really, really compelling story is basically being able to generate really, really high performance numerical kernels on the fly. So the better interface we have to the vector operations, the better, and the more useful the library becomes. Okay, so projects that are using llvm-hs, it's actually become a surprisingly common substrate for a lot of kind of emerging languages and work inside the community. Probably the biggest user downstream of the language of this tool is the Accelerate computing framework. There's a variety of academics who maintain this project at the moment. So I'm sure if you've looked at the array computing story inside of Haskell, there's an Accelerate LLVM backend, which is using llvm-hs. That's a really, really interesting project because it's probably one of the more developed array computing frameworks inside Haskell at the moment. So that's probably the biggest downstream user for us. There's the Grin compiler. Where are the guys here? Hey, okay. So the guys at Grin Tech are building a new reusable target for functional languages, and they're doing some interesting things which build on top of llvm-hs. There's Joachim's Veggies project, which is quite interesting, which is a ground-up implementation of the GHC backend in a way that you can prove some more rich properties about the code that's generated. There's the 610 compiler. I don't know if Olaf is here. I think he's out of Russia, so I don't know. And then there's the LHC compiler, which is a fledgling new Haskell implementation, which is also using the llvm-hs framework for all of its code generation. There's a bunch of interesting academic work on lattice cryptography, and there's using the llvm-hs project for the implementation of the paper. And then my other partner who works on the project with me, Moritz, is doing a lot of work on program equivalency checking, which is the process by which, given two implementations of a program, prove that they have the same functional semantics. That's an interesting problem. We do that by comparing the LLVM representation of the two programs. And then my company also works on some projects using llvm-hs, which some are open source, some are not open source. I've seen it used internally at a place we'll just call the bank on a high-frequency trading system. I can tell you a little bit more about that after, but not here. And then also there's some interesting work being done on cryptography research around zk snark generation. So if you saw my talk last year where I spoke about pairing cryptography and circuit compilation and using pairing cryptography to generate frameworks for verifiable computing, that may or may not be a thing that manifest from this year to that using this toolchain. So there's a lot of interesting things happening, and if you're building a compiler or you're looking to build a high-performance stream processing or numerical computing solutions out of Haskell, I would definitely recommend that you use llvm-hs because it's being kind of adopted as kind of the de facto standard for code generation out of Haskell. So if you want to get started on using it, I'll kind of give you the lowdown on the ecosystem. The llvm-hs package is kind of split across two different main packages. The llvm-hs pure, which is a pure Haskell implementation, i.e. you can install it from Hackage and there's no external dependencies that you have to add. It should just work. It describes all of the machinery you need to basically generate and manipulate IR as a pure Haskell data structure, including the IR builder interface that I described, all of the metadata, all of the annotation, all the printer. And then there's the llvm-hs bindings, which are actually the library that interfaces with the C++ code, which is useful for doing all of the JIT compilation, all of the optimization routines, all of the verification routines, all of the stuff that's provided by the bindings to the low-level framework. Then there's the llvm-hs preprinter, which is also pure. So if you're only generating the pure syntax tree and you want to basically just dump that out for the purpose of debugging or for offloading it to the llvm command line utilities to shell out to do that, that's a totally valid operation. That's quite useful for just taking the pure AST and dumping it out. We also have a quasi-guider, so if you want to write llvm-ar explicitly inside of Haskell code, you can do that. And there's a full parser written, there's a full lexer written that can take arbitrarily complex IR and just turn it into the representative pure AST. That's quite convenient. And then there's this llvm-hs type project, which is kind of the experimental strongly typed IR builder that we're kind of working on to kind of guarantee more correctness properties about the IR that we build. The two big projects that I want to point out that are using this downstream is the GRIN project. So the GRIN project is based on Urban Boca's PhD thesis on code optimization techniques for lazy functional languages. You guys are over there doing some great work on building basically a kind of modern STG equivalent that has a lot of nice whole program optimization properties. So it's a terribly interesting area of research that's kind of vastly underserved, if you ask me. And these guys have ambitions to build a retargetable backend for GHC Haskell as well as Agda and any other language that kind of is amenable to that kind of form. Because STG and the CMM interface are kind of a bit, they bake in certain assumptions that need not necessarily be so. So this is an interesting kind of other point in the design space that I'm happy that somebody else is looking at. And it's even better they're using llvm-hs too. So Endor and Kasaba are here. So take a look at them. We're going to be upstairs hacking on this project with them as well. So, and then Veggies is Joachim's Breitner's project, which comes out of the Deep Spec project at UPenn, which is a terribly ambitious project around taking a large set of the common compiler and code generation frameworks and creating a formal specification of them, which we can prove deeper properties than what we get today. So GHC itself actually famously has no specification. And so a lot of the work that Stephanie and Joachim are doing at UPenn is around, correct me if I'm wrong, is around getting some approximation of a specification for a large set of the entire toolchain, all the way down from GHC core down to LLVM. And that's a terribly ambitious project, which Joachim's kind of attempt to build a kind of toy, small code generator to step in that direction, which is terribly interesting, because if you were looking for a small implementation of how to build the backend for functional languages, you're probably kind of out of luck, but Joachim has written a kind of very small, kind of useful project to kind of, that's good for study and good for kind of as a starting point for building more complex abstractions. So those of you who have come from Paris or Berlin, I gave the same talk last year, oops. There's a longer version of this talk if you're interested in actually building a functional programming language backend on my website. It should be updated with all the latest llvm-hs project. So it should work out of the box, and if you're interested in basically just building a compiler from scratch, there's this tutorial I wrote like 6 years ago, I guess now, it's fun to run through if you're interested. I would encourage more people to kind of look at compiler design in Haskell. Actually, I probably don't need to encourage people to work on compilers in Haskell, but if you're interested in building native compilers rather than just another toy interpreter, because another toy interpreter only gets you so far, start looking at native code generation, start looking at actually making a backend to the compiler that can be used for real purposes, because there's a large portion of the functional language programming design space that's kind of unexplored. And what can we say about functional languages when there's basically only 2 major functional languages that are used? There's OCaml and there's GHC Haskell. And I think there's a lot more points in the design space that are unexplored, and they're unexplored because we simply don't have more compilers to kind of explore and think about what would a lazy functional language with support for automatic vectorization annotations look like, or what would there's a whole slew of things that you can combine together that we only have basically GHC Haskell and OCaml to kind of explore. And those are vehicles that are very, very useful for exploring certain subsets of the design space, but they're not going to be all things to all people. And I think if functional programming is going to survive, we need more ideas coming in the language space. And a lot of my work has basically been toward the end that the best way to encourage that kind of development is to decrease the barrier to entry to building new compilers, so that other people can basically get started on building the things that matter to them, which for the most part are the front end of the compiler, the type checker, the core AST, the specific user interface that you want to expose, and not so much the things that are like instruction selection and register allocation. And so we should have wonderful tools for building code generators like Haskell. It's like we have wonderful tools for building parsers. It's like we have wonderful tools for building type checkers. And so that's really what the goal of the llvm-hs project is about. It is online. It's all open source under a BSD license. It's partially commercially supported by myself. And we're always looking for new contributors. I think we have about 26 active contributors on the project right now. Moritz, are you here? Yep, Moritz is going to be hacking with me on the project. So if you're keen on hacking on us with us, we're happy to help you get spun up, help you get LVM installed, help you get going on building the backend for your little language. And take a look at the project on GitHub, star it, check open issues if you have trouble, and thank you.
We have some time for questions, if there are any.
Yeah, thank you. Do you have some kind of helper in this library for generating code, generating function in GHC native calling convention, such that it, depending on the platform and whether it's registerized built or not, to generate function that would be consumable by this foreign import primitive?
Okay, so you're asking whether llvm-hs provides an interface to generate functions using the GHC calling convention, which can then be invoked from the Haskell runtime system natively instead of using the C calling convention. Yes, so there's support for generating functions on the fly in arbitrary calling conventions. So all of the low-level interface for LLVM is exposed. So if you want to generate a function that uses the GHC calling convention, which happens to use, it's a GHC-specific notion about how to set up the stack when you enter a function, for those who don't know, which was added to llvm about 10 years ago by, I don't remember who wrote that, but yes, there is support for that. So basically the process by which you would do that is you would generate the IR inside of llvm-hs, and then you would JIT compile it. Then you'd have to basically tell the GHC runtime to basically invoke its jump instruction, to basically jump into the JITted memory, just like it would a normal function that was compiled by GHCI itself. But there should be no reason why you shouldn't be able to do that. You'll probably need to do a little bit of manual inline STG to do that, but I don't see any reason why you couldn't. In fact, I'd be happy to sit down and talk with you if you want to try that out. Over here. Sorry, I can't hear you. Have I considered using the singletons library? Have I considered using the same terminology as singletons library? Yeah, the kind of mechanism by which we're enforcing a lot of the construction for the IER is kind of structurally it's singletons, right? We're taking these things, lifting to the type level value where there's a single type and then it's manifest and you can pull it back down to the value level. Yeah, structurally they are singletons. The singletons library requires a lot of like template Haskell to generate all of this machinery versus the library that we implemented this, it's probably tops, I'd say 150 lines of Haskell code to do this. So it's quite simple. And some of the conventions that we're using around, say, the get element pointer instruction, which is quite non-trivial to implement at the type level, requires some custom machinery that might be a bit of a pain to implement inside of singletons. But I'm open to, if there's some way to abstract over the two in a way that reuses some code that exists, that would be a cool project to be worth hacking on. Goes with the name, right? So we have the type family here, which has as its first argument a type, a name, a symbol, and a nat, all of which are not going to unify to the same, right? Because you need polykined over both type level strings, type level natural numbers, and type level data kinds, right? Makes sense? It's actually terrible. It's only like 150 lines of code, and it's a little polykinded, but it's not terribly gnarly. I do have a lot of abandoned, intermittently maintained projects around compilers. Okay, so the question is, what is the right approach for targeting WebAssembly from Haskell? The first answer to this is, I don't know until it's been done. The second answer, I've talked about this with a lot of stakeholders. There's currently about 4 or 5 kind of WebAssembly projects at the moment. I think it's a terribly interesting idea, actually. And I think having a WebAssembly backend would eliminate a lot of the kind of blow up that we've seen in kind of Haskell to JavaScript implementations that are kind of fragmenting a lot of things. If we just have one retargetable backend which could target the browser in any way possible, I think that's a good idea. As far as going through a GHC's LLVM backend into WebAssembly, I think that's probably not a great idea just because of how kind of gnarly the GHC LLVM backend is, and it uses all sorts of kind of bizarre calling conventions and ways of setting up memory that are not going to be terribly efficient in the browser. So if I were to work on a WebAssembly or a Haskell 2 WebAssembly project today, I'd probably target from the STG level and figure out a optimal way from going from a spineless tagless G machine down to WebAssembly, and then that would give you most of what you would want for free. But I actually would not go through LLVM just because of how weird the LLVM backend of GHC is. Does that make sense? So there's the TWEAG project, which is working on this as well, which I think is not going through LLVM. There's one that's the Web GHC project, which is going through LLVM. I'm curious to see if that actually works. I have my doubts about whether that'll work, but and then there's another firm out in California that's doing some sort of restricted subset of GHC, which is a custom implementation down to WebAssembly, which I think might be interesting, but I think it's not going to be able to reuse a lot of the standard GHC machinery then. So I think that's going to have a limited shelf life. So.
The speaker again.
Okay.